This is our second lecture for Chapter 5, and this one's pretty meaty. We will do a lot of work with this in class. We've already talked about forces and interactions. Now we're actually going to talk about Newton's third law of motion. The next video will look at vectors, and we will summarize what we've learned. So here's Newton's third law of motion. The third law of motion is that the force, any force, has an equal and opposite opposing force. All right. The important thing to pay attention here is that we are talking forces. We're not talking velocities, we're not talking accelerations, we're not talking positions. We are strictly talking forces. We will remind ourselves about a lot of different ways that we look at how that force changes our position, our velocity, how it relates to our acceleration. But the third law is specifically talking about forces. So you're a soccer player, you kick a ball with 1,500 newtons of force. What is the reaction of the ball against your foot? Is it less than the force you used to kick it? Is it the same as? Is it more than the force you used to kick it? Is it something else entirely? What do you think? Well, in fact, Newton's third law tells us exactly that the force of our foot on the ball is the same as the force of the ball on our foot. These two forces, it's not very accurate. People will call them an action force and a reaction force. That kind of infers that one comes before the other. They're happening at the same time. So maybe think of it as a pair, not so much as an action and a reaction. They are a pair in a single interaction. This all happens simultaneously at the same instant. And the force does not exist without the other. They are equal in strength and opposite in direction. Remember that we are talking about the force, not the velocity or the acceleration or the other things we measure with vectors. And they're always acting on different objects. We'll always be very specific at identifying the objects involved when we look at their interacting forces. As an example, why does your car roll? If you have ever driven on ice or tried to drive on ice, your wheels can spin and you can go into a skid. So your car rolls because the tire pushes on the road, and then the road simultaneously pushes against the tire. There's friction between the two surfaces. Your tire needs a grip to push the car forward, and that is the force involved. That's why your tires wear out. That's why you see skid marks on the ground. Is the interaction of the surface of the tire with the surface of the road. So Newton's law tells us that for an action, there's an opposite reaction. In our case, the road pushes the tires forward, and the motor of the car pushes the tires. The tires push backward, the road pushes forward. I'm sure that you've blown up a balloon and not tied it and let the pressurized air shoot your balloon across the room. Same thing with a rocket. In the case of a rocket, there's a chemical reaction going on inside that is pushing exhaust out the back. So the rocket pushes on the gas, and then the gas pushes on the rocket. Here's a rule to remember. When you are trying to identify your action and your reaction, it's two things and it's a point of contact. Identify the interaction. One object exerts a force on the other. The second exerts a force on the first. They're happening at the same time, equal magnitude, opposite direction. And we are only talking about forces. Here's chapter 2. What's a force? It's a push or a pull. All right. Here's a tough one. You step off the curb and the earth pulls you toward it. That's gravity. So that is one force. What's the force pair and what's the opposing force? What's the reaction? Does the air resistance count as the reaction? Is it non-existent? Do you pull the earth upward? Is it none of the above? This is kind of a trick question. But the force of gravity. So you are exerting a force onto the earth. What is the reaction? The trick is in the language. So it is between the two objects are you and the earth. The force is you are pushing the earth with your weight. And according to Newton's third law, you are pulling the earth upward toward you. All right? What's your reaction to this? People don't like this one. And remember from Newton's second law is that our acceleration is equal to the force divided by the mass. So in the case of the earth, your force, the force of your weight against the earth is so far overshadowed by the enormous mass of the earth that the acceleration exists, but it is in fact unmeasurable. So teeny tiny. Can you not sense that the earth is moving up toward you? Why is that? Is it because the earth cannot move? Is it that the earth can move, but it's reacting to other objects instead of you? Does the earth in fact move, but at an imperceptible amount, or none of the above? So this one is challenging. Can you believe something that is opposite of what all your senses tell you? Can you believe that the earth is moving toward you, even though there's no way for you to perceive that? The forces are the same. The force that you're exerting down on the earth is your weight. Your movement, your displacement is greater, and it's because of the relationships of the masses between you and the earth. Hopefully you are okay with the idea that the earth is much more massive than you are, and that your mass is negligible compared to the earth's. The opposite of that is that the reaction force is there, even though you can't feel it. Let's look at a better idea. Let's shoot a cannonball. All right, you got some high power graphics going on here. If you've ever shot a gun, or even the Nerf guns that we play with, there's a recoil that even though the projectile goes forward, we feel the gun go back into our hand, and that's because of the interaction between this system. Now remember, we want to be very specific, so we are looking only at the cannon and the cannonball. Those are our two objects. We're not looking at anything having to do with the Earth, with air resistance, with friction. We are simply looking at the system between the cannon and the cannonball. Uh, things like cannonballs and bullets move because of a chemical reaction inside the cannon. There's a very rapid expansion of gas because something has exploded. That pressure pushes the cannonball out. That's how a gun or a cannon works. In our case, the cannonball, well, Newton's third law is telling us that the magnitude of this force is the same, but the directions are opposite. So think about the massiveness of the cannonball compared to the much greater massiveness of the cannon. And what does that do to our acceleration? Well, if we have a large number divided by a small number, will be a little bit larger, but when our force is divided by a very, very big number, that makes our acceleration quite small. Another way to look at it, a force exerted on a small mass gives us a large acceleration. A force exerted on a large mass gives us a small acceleration. And that is because of Newton's second law, how we define what acceleration is. All right, you try one. Why is it that the acceleration of the cannon and cannonball are different? It's because the forces are acting at different times. It's because the forces are not really the same. Is it because the masses are different? Is it because the ratios of force to mass are the same? Why is it that when the cannon is fired, the accelerations are different? It's all about the masses of the objects. The mass, the very, very, very large mass of the cannon and the relatively tiny mass of the cannonball. Let's look at another one. You are driving along very quickly, and there's a bug, and you splatter that poor bug all over your windshield. What's greater, the force on the bug, the force of the car on the bug, or the force of the bug on the car? All right. Is the bug experiencing the greater force? Is the car experiencing the greater force? Are they both the same? Or is there not enough information? Where is the force bigger? Oh, the poor bug in the car. You know exactly how this story ends. In terms of physics, the force on the bug is equal and opposite to the force on the car. If they're the same, why are the effects so very different? There's your question. Well, the answer to that has to do with the mass of the bug. The mass of the bug is very, very small, and the mass of the car is very, very big. The acceleration, the change of acceleration for the car is not noticeable. The change of the acceleration for the bug is fatal. We will talk more about this in future future chapters. Let's go ahead. So you and I have the same mass, and we are on slippery ice, and we push each other. We put our hands together, we both push back. What do you predict happens with our speed and our directions? Will our speed and direction will we have the same speed in opposite direction? Will we have it so long as we both are equally strong and one of us does not push harder than the other? Will we not be at the same speed or opposite directions? Will we not be that way unless there's some acceleration occurring? Right, we are ice skating, we push off from each other. We, in fact, do move at the same speed in opposite directions. Here's your example. It doesn't matter what the differences are when you're pushing. Take, for example, push your two index fingers together. Push your left one into your right and the right one into your left. Now, you might be using more muscle with one than the other. You might be thinking you're moving it, but after you've pushed against each other for a while, look at your fingers, and in fact, they're discolored and mashed in the same amount. So the reaction between the two objects is always equal and opposite. The trick to this question is that we have equal mass. So since we have equal mass, and since we already know that our acceleration is equal to the force divided by the mass, our forces are equal and opposite, our masses are equal, so our accelerations will be equal and opposite. I'm going to stop here and do the rest of this segment on a separate video. This is getting a little bit long, so I'll check back with you in a bit. Thanks, bye.